look at some of the basic concepts in material science, and then in this class, so supposed to be 9:30 to 11, so at 11 o'clock, I will cover the fundamentals of material science, and then in the afternoon, I will start with magnetic materials. Okay, so it is difficult for me to cover all the fundamentals of material science, but I will just go over a few concepts. Right. So, what is material science? It is, of course, a field of study, but what does, if you break it down further into more fundamental level, so what does it cover? So it's made of some other fields, right? Like material science is not a foundation field in itself. It's a combination of different fields. So when you think of material science, what do you think? What comes to your mind immediately? Anyone? When somebody is talking about material science, what do you imagine?
Composition.
Yeah, compositions, right? Making different materials. I talked about environment and chemistry. So it's the compositions. So which is nothing but chemistry, right? So when you are making a new material from two different materials, that is, you are adding two chemicals to make it another chemical. So when you are dealing with only compositions, you are basically dealing with chemistry, right? So again, in order to understand chemistry, you need to go even further down to atomic level, how the bonds are forming and how the hybridization of the bonds occur, and how the electrons are shared, what is the type of bonding, covalent, ionic, and so on and so forth. That is even further fundamental concept. But that's what guides your composition. How do you know whether you get a new composition when you add two materials? Is based on the bonding, right? How the electrons in the valence bond pair with the other electrons of the other atoms, and that is composition. So it involves composition. So that is chemical makeup of the materials. And then it's not just it. Once you make a new material, that's not the end of it. Material science is much more than just making a new chemical, right? Or new composition. So which is the structure of the material itself, meaning not the structure as in the geometry of the material, but the more fundamental level, like how the atoms are arranged. Are they making regular structures? Which means, is it a crystalline? Is it an amorphous? Is it a polycrystalline? Is it a single crystal? That is the structure. And that structure determines the properties of the material. So steel is, you can have same steel but different strength, right? Chemically, it will have the same amount of iron, it will have the same amount of carbon, but the strength will be very difficult. One is you can't apply as much load as you can, but it won't bend. The other one will be very flexible, right? So that is because that is possible. Different properties, not just mechanical, also electrical. Your transformers and your adapters, when you plug in, they have iron cores, and so many fans have iron inductors, and those are electrical steels. There is structural steel, electrical steel, right? And they may have the same composition, but their electrical properties and structural properties will be different depending on what is the crystal structure, morphology, and the atomic structure. You can have the same composition in different crystal structures. So that is the structure. We have to first come up with the right composition, then the right structure, and then using these both relationship structure and chemical composition, you design the process, how to make this material, right? So that is processing, and this is the structure, and when you process with right structure, you get the right properties. So this is called material optimization, or material engineering is basically nothing but taking the right composition, right structure, and having the right process to get the right property. Okay, that is what is materials engineering. Okay, material science, and usually it is always wherever you find materials engineering branches or field of studies, it's material science and engineering. They say. Okay, because there's a lot of engineering to it as well. So this is the material science. So we will be looking at not just composition, but also structure in order to get the right property. And of course, chemical composition, you probably are familiar, you think that is the main determinant of property, but it's not just that, but it's also the structure, crystal structure, morphology, and then how you process it changes the crystal structure. Okay, and processing usually doesn't affect the composition that much, but processing affects the crystal structure a lot. So here is the history of materials, and if you look at the strength of the material, as you see through the history, around 1800s, when they learned how to make steel with carbon, different types of steels, there was cast iron, which was strong, and then when they learned how to make certain steel, it was the strength increased. And then when they started to make composite materials, the strength, of course, strength per density. If you make a very heavy material, the strength can increase, but strength per density is what is important. So the new composites, polymer composites, the carbon fiber composites, along with metal fibers inside, their strength is quite high. And see how the strength of the material suddenly increased when you understood how to. This is all engineering. When you deal with composites, you're not dealing with atomic level anymore. You're not dealing with crystal structure. Now you're just dealing with the processing, alignment of different fibers and so on and so forth. So that is pure engineering. So material science first was composition. Maybe they create a lot of composition here, and then the structure, and then now the engineering, right? So this is how we can, the future, of course, engineering at a smaller level, which is nanomaterials, and using functional materials further to increase. Not just you increase the strength, you can increase the strength maybe when you apply an external magnetic field or a current, the strength even goes up, right? That is possible. So those are again, no one has done it yet. This is just thinking out loud. There might be materials wherein it has certain strength, which is already somewhere here, and maybe they are responsive to certain electric field or magnetic field or light. You apply light and you rearrange the atoms because these materials are sensitive to light and electric field, and they rearrange the atoms. Those would increase the strength even higher. That means that we use functional materials that respond to these external stimuli. Okay? So if you classify the materials, they are generally classified into these four categories: metals, semiconductors, ceramics, and polymers. Metals are quite widely used for engineering materials, semiconductors and electronics, ceramics for high temperature applications, and also some functional materials are ceramics. PZT, Um, have you heard of piezoelectric materials?
Yes.
Do you know which is the most common piezoelectric material? PVDF is a polymer, yes. Yeah. And what the most commonly used one is called PZT. P stands for lead, PV. Z is zirconium, T is titanium, so it's lead zirconate titanium, titanate. Okay? So it's the ceramic. So and then we have polymers, that is polypropylene, PDMS, PVDF, some cellulose-based polymers, hydrogels, and so on and so forth. Okay? And then here is the new combination of all of these can be made into composites. So now, if you think you need a certain property of ceramic along with metal, but you need some flexibility, you can combine all these to make a composite material, which is combination of all the materials. So, does anybody know if composite is so good, why is it so less used? Does anybody know why composite is not so widely used? I mean, now Boeing 787, I think, has about 40% composite in its structure. But why it's not so widely used? If it is so good, why do we even need to use metals?
Weight.
Sorry?
Increase of weight.
Weight. No, but composites, you can make a lighter composite.
Bending strength.
Cost.
Cost, but you can
Bending
also, sorry?
Bending strength. Low bending strength.
Bending strength. Well, no, I think you can increase the bending strength. But even if you achieve bending strength, if you achieve cost, what do you think is one of the limiting factors? The limiting factor, right?
Microstructure, I guess, cannot be altered.
You can. I mean, you go to individual ones, and then because individuals are the metals, ceramics, and polymers, right? You can alter their microstructure. Yeah, kind. But there is one factor that allows that's hard. That is limiting anisotropy. But yes, that is true. But what does that do? I mean, yeah, but so it is hard to predict the strength, right? You have so many combinations. I mean, if you don't know when it fails, how much load you can put, what's the use, right? If you want to put it in an aircraft, you need to know what is its load capacity and how reliable it is. What is how many number of cycles of fatigue it can take, right? If you don't know that, then it becomes hard to use it, right? So people will say, no, aircrafts have to be really reliable, and so do the space shuttles and rockets. And if you don't know what are the exact strengths, then it's hard to model them. Nowadays there are techniques, but as the layers go higher, the number of layers go higher, it becomes difficult. So it's difficult to predict. So that is one of the limiting factors. But I hope with the new machine learning tools and increasing the computational resources, high power, quantum computers are also have high capability of computation, meaning you can consider each and every atom in all of them and predict its strength. But it needs huge computational power. You need supercomputers to do that. But if you have that, then yes, you can predict its strength. Right? So that's now scale of things, right? In material science, again, we mainly nowadays we operated at the macro scale. Then now we are doing the nano scale. So here is the natural materials in different scales. Here is the artificial ones, and at nano scale, we operate nowadays. So, do you know your laptop? It has an i7, Pentium, Intel i7. How many number of transistors it has? It's about 100 billion. The new i7 processor will have 100 billion in a single inch by inch square. 100 billion is a large number. You can't, it's hard to fathom, right? We don't deal with such numbers in day-to-day life. Well, what that means is the distance between the source and the gate in the transistor is close to around 2 nanometers. So that's the level of engineering we are doing right now. Okay? So 2 nanometers we have to put an electrode, the metallic structure, every 2 nanometers to make this number of transistors. Again, for how many of you have electrical background? No, oh yeah. No. How about material science and mechanical and physics? Like most of us. So when I teach our undergraduate students I teach mechatronics and robotics, and when I tell about transistors, and they are like, oh, it's far away from us. We don't need to know. Looks like a very complicated electrical device, an electronic device, a transistor. But if you think about it, how a transistor is made, it's just 3 layers of semiconductor materials. It's silicon, basically. Same 3 layers of silicon, but they are doped in a different concentration of different elements. So if you go to Intel foundry, Intel factory, where they make all the chips, half or even half of the engineers are material science engineers. A lot of our mechanical and nuclear engineering PhD students end up in Intel. It's ironic, right? So it's a chip, which is an integrated chip, which is an electronic device, but it's done by the fundamental work is nothing but material science. Okay? So, and naturally, atomic level, if you look at a peacock's feather, the blue color doesn't come from blue pigment. It comes from, it's actually different color. It's not blue color because it has so tiny variations in its structure. It diffracts light in that fashion, so you see blue light. Okay, so that's not if you crush the feather and make a powder and make a pigment, you won't get blue color. Okay, it's nanostructure in nature. Okay, so that is the material science. We can do from at a micro scale or macro scale. Micro scale, we are doing it in our phones, laptops, right? In nature, it always existed. Okay, so that's what we are basically. We want to do that, right? We have to be at all scales. So now let's go to smart materials. So what are smart materials? Or functional materials? Okay, it's interchangeable. When we say smart materials, we do that functional. What are functional materials? Basically, when there is a coupling between 2 domains, that is, you apply stress and you measure electrical stuff, which is voltage or electric field or current. You apply stress and measure thermal properties, right? So there is a coupling between mechanical, electrical, thermal, optical, magnetic. So when you change one property and get change in the other property, that's what we call it smart function, right? So that is the coupling, basically. And of course, if you actually think about it, most materials can be made into smart materials. But because if you change the structure of the material, or if you apply a force, you're basically applying stresses to the crystal structure where you are bringing atoms closer in the crystal structure, right? You are changing the lattice parameters of the crystal structure. And when you do that, and of course, the electric field also changes in the crystal, which results in some variation in the electric property. But for a lot of materials, you will not see it. If it doesn't change the electrical property, its thermal properties might change. If its thermal properties doesn't change, its optical properties might. Something has to change, right? So we can actually make a lot of materials functional materials, but some amplify it. Okay? So those we call functional materials or smart materials. They're very useful because a lot of the time we like certain materials, but for example, polymers, they're normally insulators, right? And can you imagine taking a polymer, applying stress to it and getting a current out of it? No wires, you're not supplying any current or anything. Just whack it and you will get a voltage of it. That is possible. These are called piezoelectric polymers. They are PVDF. They are not very expensive. You get PVDF pipes actually. But you need to do some engineering to make PVDF pipes to a piezoelectric polymer. That's what is called polymering, which we'll talk about in later classes. Okay? So, if there is a coupling between two or more different properties or fields, physical domains, then we call them, those materials, as functional materials. So you know now what are functional materials, right? So you apply something, you apply stress, get change in chemical, apply stress, change in magnetic field and magnetic flux, apply stress, change in temperature, apply stress, change in current or electric field. These are all useful parameters that you need, right? It's easy to apply stress, and also it's easy to apply temperature, right? So, and now you can apply electric current. It's easy to apply electric current because we generate it circuitry. Right. So that's the coupling between mechanical, electrical, and thermal. And if you have magnetic, optical, chemical, it becomes just complex. Here is, I just grabbed a diagram, I just draw this. It existed, I thought it would represent nicely. So if it is mechanical and electrical, you get piezoelectric. Direct piezoelectric, if you apply this way, stress and measure current or voltage, that is direct piezoelectric effect. But if you apply voltage, and if you see change in the dimension of the material, that is converse or inverse piezoelectric effect. You apply electric field to get rise in temperature of a material, it's called humidity. And if you apply temperature to a material and you see change in the current or voltage, that is pyroelectric material. Okay? Pyroelectric effect. And similarly, temperature and mechanical stress. So if you apply temperature, the material expands or contracts. That is coefficient of thermal expansion. And I don't know why these two arrows are the same way. If it is different, if you apply mechanical stress, you get temperature change. These are caloric materials, elastic caloric. So you apply stress and you get a change in temperature. Okay? So here are some examples of piezoelectric material, piezoelectric material, shape and realize, magnetoelastic materials, magnetoelastic materials, magnetocaloric materials. See, whenever there is magneto, it's magnetic field, right? You change magnetic field and you get rheology is changing the viscosity, right? And elastic is changing the chemical, changing the N's modulus or changing the mechanical properties. Caloric is changing temperature. This is magnetocaloric. Electrocaloric is you apply current and you get changing temperature. Barocaloric, apply pressure, you get changing temperature. So elastocaloric and barocaloric. Elasto means change in stress, baro is change in pressure. Stress and pressure have the same units, right? But it's the way you apply. So some are called barocaloric materials, some are called elastic. Then there is thermoelectric materials, thermochromic materials. You apply temperature, you get a change in color. And that is because its optical properties change. Those are, think of it, it's all like magic. You know, if I show somebody a red polymer or a metal by holding at the bottom and then hold it on top and provide my body temperature, and when it crosses 37 degrees centigrade, it changes its color. Looks like magic, right? That's what people, when they didn't know how the magnetic materials worked, there were a lot of magic tricks around magnetic materials, right? So, monochromic materials change in color due to the light. Electrochromic change in color when you apply electricity or voltage. So these are all different materials. But it's just theoretical. Let's see how many of you, can somebody name or where have you seen a piezoelectric material? Have you used a piezoelectric?
Yes.
Yeah.
I think in Japan they are producing electricity from walking on streetways.
Yeah, so I worked on that too. I mean, you are going something very novel.
Stove,
Day to day life.
the stove lighter.
Stove lighter, yes,
Yeah.
lighter. Yeah. Because when you apply pressure, it basically electrodes spark together. The electricity is so high that you get a spark and that lights the this one. What are the piezoelectric?
Portable nebulizer.
I'm not familiar with nebulizers. So could be, yeah. How many of you have used a quartz watch?
Hmm.
An automatic watch?
Hmm.
Now these are all digital. But earlier we used to have these quartz watches, right? Now, even now, quartz watches are digital watch. Quartz is nothing but a piezoelectric material. What you do there is in quartz, the quartz crystal is finely cut into a tuning fork, literally a tuning fork. It's laser cut, they cut it and tuning. They cut it and they keep cutting and keep listening to the frequency. And when it hits 1 second, there is certain frequency that it, then it's used for quartz watch. They cut it such that the tuning frequency, oscillating frequency is 1 second. Okay, so that is the quartz. And pyroelectric materials, probably a lot of engineering applications. Shape and realize, again, these are all, they look like they're fancy materials and they're not quite widely used in day-to-day life. Shape and realize. So Dr. Somshekara's lab has worked a lot on shape and realize. So there, I think his first PhD student who graduated, his thesis was based on shape and realize. So we'll, that's, what else? No, yeah. So you may not have come across all these materials because they are still known materials. Okay? But they have a lot of potential to do, that can be used to solve many problems, engineering problems, if you use them right. Okay? So let's look at one really fancy material. I think this nitinol, it's quite widely, okay, shape memory alarm. Nitinol is a shape memory alarm. I'd like you to listen to this video. If I explain, I don't do justice to its importance. Oh, it's going to be a problem because I'll have to turn on the audio.
Yes, sir. You can do it, please.
So shape memory alarm. Remembers its shape. What that means, what he showed there, I don't know if everybody understood it. Take this shape memory alarm, SLA, take it to 500 degrees centigrade, which is its transition temperature, and then convert it into certain shape. Right? And when you are at 500 degrees, you make it to a certain shape and you quench it. So when you quench, it becomes room temperature. Now you remove its shape, right? You stretch it and it becomes a thin wire. And now if you go and heat it again, it will go back to its shape. So that means when it's at 500 degrees, you make a complex structure, even a Taj Mahal wire frame, right? And now you quench it and you remove all that, right? You make it as again a wire, put it on the board and heat it again, go back to Taj Mahal shape. That is the shape when we're talking about. So that's nothing magic. It's just going back to, it remembers its shape, goes back to its original shape. That is the shape will be allowed. Okay, so this 500 degrees, it'd be difficult to work at 500 degrees, but you change the composition and we can bring down the transition temperature close to whatever temperature we want. It has a tunable transition temperature. By changing the composition, you can bring down the working temperature, or what it is called as the phase transition temperature. Okay, so that's what it is. thinking of an actual device, right? Or a sensor is also some sort of semiconductor device, but just a metal wire can act as a sensor or an actuator. Right, so now, so do you know what is nitinol chemically? Yeah, it's in the name, nitinol, right? So just imagine those three elements came together and made this really cool halide. How many more such materials are hidden in these 118 elements? Right? We barely know many of these elements. We just operate here because those are more abundant. Right? As you go down here, they are there on the Earth's crust, but the usage has been limited. Neodymium is the new neodymium iron boron magnets. We operated here. This itself, all these materials, they themselves, this is responsible for silicon and germanium, responsible for our semiconductor revolution. Imagine if you go down, right? That's why I say if there is a problem, there is a solution here. So if you know your periodic table very well, if you know your material science well, you can get a property you want that will solve some problem that could in turn solve a societal challenge for carbon capture or for some medicine and so on and so forth. For example, the stents came from nitinol, right? The stents that go into patients who have heart attacks, they are made out of nitinol because they're super elastic and they're actually small at room temperature, and when it goes to 37 degrees, they expand. Right? So such cool things can be made through so many other materials. We just need to explore. Right? That's why I say material science is really cool, but it's a lot of work. Right? So, yeah, some people are so passionate about it, they know all this by memory. All the elements, 118 elements. Okay, so that is the composition, that is the chemistry, right? The shape memory lies not chemistry. It's chemistry, a little, but also structure. Now, let's go to pure structure. Are you familiar with polymorphism? So basically, it's a ability of the same chemical composition to occur in multiple crystal structures. Okay? For example, ion system, that is iron and carbon, can occur in BCC, FCC, as well as this BCC is different than this BCC. This is called delta ion, gamma ion, and alpha ion. Okay? This exists at very high temperatures, medium, and low temperatures. So, how many of you are familiar with phase diagram, iron carbon phase diagram? Right? If you study material science, you have to know that. If you understand iron carbon phase diagram, you will understand how amazing or how cool is material science. Here, this iron can exist in different crystal structures, and not just different crystal structures, but also when they are in mixed phase, they form different. There is crystal structure, then you alloy them, because when you add carbon, you are basically putting it in a crystal structure, these carbon atoms, interstitial sites. They're putting these carbon atoms and changing its strength. So the atoms, when you apply a stress, they normally move at certain strength and create dislocation and plastic deformation. But when these carbon atoms come into their gaps, their strength changes. Okay, that's what we are doing here. And when you have different phases of the mixture of these different alpha, beta, alpha, gamma, and delta phases, then again the property changes because now you have slightly different microstructures. So all these are different microstructures: perlite, bainite, martensite, spiridite, tempered martensite. All these are different steels. Their strength changes, their chemical stability changes, their ability to take impact changes. Okay, so these are all different forms of steel, and the ductility reduces as you go down like this, and the strength increases as you go up like that. So you can engineer a material specific for your application. Swords need certain, this one. Bridges need certain strength, and rail tracks need certain strength. So you can change it, and it's easy. You vary the carbon content. So you're talking about only 6.7% carbon content. This is the binary phase diagram. Okay, here it's all liquid, and here it's liquid plus solid, liquid plus solid. Here it's solid, with two different forms of solid. So it's a mixed phase here, mixed phase, single phase, mixed phase. So depending on how much carbon you put, and also you can do thermal treatment. You go here and suddenly quench it. You block this structure. Okay? So there's so many things you can do, and they all result in, and they have done for ages. That's how we have so many varieties of steels, right? So this is perlite structure, which is a very popular structure. And now that was the binary phase diagram, iron and carbon. But if you do tertiary or ternary, you have three, for example, copper, aluminum, and silver becomes complex. Then there is quaternary, four materials, even more complex, right? So there is something called high entropy alloys. They have 5 or more elements. So you are basically increasing in complexity, but you're getting desired properties, really cool properties that you can't get with 1 or 2 elements, right? So there is a lot to explore there, okay? It's a, what we call as wild west, even unexplored, right? There is so much you can do. So now let's come to the crystal structures. Again, I don't know if this is fundamental. So basically how atoms are arranged. These are different types of crystal structures. And if you have cubic, you have a nice symmetry, and you can have all these type of different arrangements, which you are proudly studied in your basic. And the link here works only for those who have bought the canister book. So you could explore different type there, but ignore that slide. And now you can calculate the theoretical density if you know the crystal structure. So basically, what is density? Density is mass by volume, right? So if you know the crystal structure, that means you know the lattice parameter. Lattice parameter is basically this one dimension. And if you know what structure it is, if you know the lattice parameter, you know you can calculate the volume of this. And if you know how many atoms are there, And if you know their molecular weight, atomic weight, sorry, if you know their atomic weight and how many atoms are there, you know their mass, right? So that's what it is. So this is number of atoms. This is a BCC. BCC is 108 by 8 multiplied by 8 plus 1 body center. You get 2 atoms in BCC. FCC we have 3, right? And simple we have 1. This is the atomic weight. 52 is for chromium, and divide by AQ, that is the volume, but divide by Avogadro's number will give you theoretical density. Okay? So now my question is, how will you determine A and the crystal structure? How do you know certain material? If you have a material you want to determine theoretical density, how do you know the lattice parameter? Now we know what structure it is. If I give you a piece of metal and say, can you calculate the, I don't know anything, okay, please calculate its theoretical density. What will you do? You need to those parameters. How do you get that? A and crystal structure type, BCC. Any guess?
So different techniques are there, like for exact from XRD we can get this.
Yeah. So you get lattice parameter from XRD and you know the crystal type BCC by XRD. XRD is X-ray diffractometer. Are you familiar with XRD? I know PhD students are, they do it day in and day out. Okay, so XRD is a technique where you can determine what type of crystal structure and what are the distances between atomic layers. So that is XRD. Okay, so XRD is X-ray diffractometer, and it is governed by principal law called Bragg's law. ID equals sorry, 2D quantity equals n lambda. Okay. So lambda is the wavelength. So what happens is when you put X-rays on a material, X-rays go and hit the atoms and get deflected. So some X-rays hit the first atom and go there, and some X-rays go and hit the second and go and sensed by the detector. The detector is basically a sensor that senses X-ray. And there is a difference in the path when the detector senses the X-ray, and that distance gives you the lattice parameter. Okay, so that is your D. And n lambda is usually n is 1 because you get most of the deflections within 2 layers. And sine theta is theta at which this is the theta, the angle of incidence. That is the theta. Okay. So lambda is the frequent wavelength of the X-ray. Okay. So this will give you V, the spacings, and the spacings. And the patterns here will tell you whether it's a BCC or FCC or just a simple qubit. Okay. Once you know what type of crystal it is, what is your lattice parameter, you can calculate its theoretical density. You can also do a lot of other calculations. You can even find out its crystalline size or its grain size. You can even calculate where if there is any residual stress inside. Okay, this is how it looks like. It's so clean that this is for single qubit. If the lattice is crystal structure is really complex, like monoclinic, then you don't get this thing of peaks. You get multiples of those peaks. Okay, here is each peak represents a plane. Okay, And if it's an amorphous material, if it's not crystalline, you get XRD result will show you no patterns like this, no peaks like this, because the X-ray when X-ray is detected, there is no pattern, there are no align, right? There are no layers of patterns, so it doesn't get that D parameter. You have to have that D parameter in order to get constructing interference for the detector to see these peaks. So here is quartz. Okay, quartz is autonomic. Quartz is monoclinic. The crystobelite, which is another form of. So this is same chemical compound, SiO2, nothing but sand, right? Your sand can exist as a glass, or sand can exist as a quartz that can go into your watch as a piece of electric material, or crystobelite, which is not piezoelectric, occurs in completely different crystal, whose properties will be very different than glass, quartz. Okay, so that tells you how just changing the crystal structure will give you different properties altogether. Right, how are we doing? I have 7 more minutes before you can take off for break. I want to see. Okay, I think I should be able to do that. Right, so now you looked at crystals and how crystals affect properties, right? And you know how crystalline parameters, the parameters from the crystal can determine the density, can determine its electric property, magnetic property, strength, thermal property, optical property, and so on and so forth, right? Now, that's the atomic level arrangements we finished the composition, now atomic level. Now we have to do the engineering part, the processing part, right? So when you melt a material, so let's look at simple example of iron, right? When you take iron and melt it at 1600 degrees centigrade, 1650, it becomes liquid. When you start to cool it, what happens? It first becomes that delta phase, gamma phase, and alpha phase, right? Cools down to different crystal structures. But do you think it will all become one crystal structure? And all the crystals are aligned and have one nice single crystal? No, right? Because there are some impurities. It's impossible to have a perfectly pure material. Any small impurities will disrupt the crystal orientation and will grow in different forms. And you see grains, right? In I don't know, when we were kids, we used to have some aluminum type of buckets that had these really large grains. And even some pipes have these grains that are so big, it's like almost 5 centimeters size grains. Those are single crystals. Each grain is a single crystal. So when the crystals start to form, they grow if it is perfect condition. They all will grow and grow in one single grain. You get single crystal. But if it's not perfect, you get large crystals, small crystals, and multiple crystals in different directions, right? So when you have single crystal, if you really control everything and grow it really slowly so that all the crystals orient in one direction. So if it's this is what? Body center, right? So this body center cubic crystal is left to grow, each will stack on and get nice alignment of single crystal you get. So if you have a single crystal, what do you think will happen to the properties? If you measure properties, so if you pull this tensile, if you measure tensile strength along this direction, right? What will be the strength, Young's modulus versus if you pull it along this corner to this corner? Which one will stretch higher? Yeah, so diagonal or this one, again, it depends on materials, but they will have different properties in different directions, right? So that's one example of tensile strength. But same is true for electrical. If you apply a voltage from here, this corner to this corner, the conductivity will be probably higher here because the distance, bond length will be smaller here. Okay? Likewise, bond length, bond energy will determine a lot of material properties. Okay? And by changing the crystal, you can get different material properties. So you will have a different material property along the diagonal than the side. Okay, so that is anisotropy. Okay, so you get different properties in different directions, right? So if it's a single crystal, then yes, everything is well aligned. So if you take a material and you measure tensile strength along its shorter dimension, you'll get one property, but if you measure along longer axis, you'll get another property in a single crystal. That's because they're all aligned in one direction, right? So that is single crystal. But it's impossible to get single crystal in a furnace in industrial scale, right? So you get all these different crystals oriented in different directions. So what happens if you take all these small grains, which are, each grain is a single crystal material, right? So have you seen these grains in any of the example I gave in pipes? You can see sometimes these large metallic pipes, you see the large geometric features that come on the surface, especially if the metal is polished. So those are grains, nothing but grains. In those grains, each grain is a single crystal. Okay? And some materials can have large single crystals at a given processing parameter, and some materials can have smaller. So these polycrystalline, when they're all aligned in one direction, what happens to your anisotropy? There is no anisotropy because everything is aligned, it all becomes a combination, right? So wherever you measure, your strength, Young's modulus, or the conductivity will all be the same. So the polycrystalline samples are not anisotropic, okay? So there is no anisotropy in polycrystalline samples. Right, so this is when you take an ingot, when you pull a liquid, and when you take an ingot and cut open, these are the grains, okay? So that's how the grains are. Each grain is a single crystal. They're all randomly oriented. So now the last engineering part. So I talked about how composition can determine the properties, how the atomic arrangement can determine the properties. Now the processing parameter of single crystal versus polycrystalline, right? The other one, other engineering method or engineering of material is engineering the defects in the material. And as I said, it's impossible to make a material that's perfectly pure. So you will invariably introduce lots of defects in a polycrystalline or crystalline material. So when the crystal are, when the atoms are aligning, sometimes there might be a missing atom. Sometimes when it is aligning, it might just align in a slightly different direction. So these are all different defects, okay? So the type of defects are vacancy atoms, interstitial atoms, and substitutional atoms, and dislocations. So these are point defects. Dislocations are line defects. Does anyone know what is the other defect? There's another type of defect. So these are point defects caused by missing atom or impurity coming in like carbon, or instead of iron we find cobalt. That is substitutional. These dislocations are lines, like the arrangement is this. Which one? Slip is due to line effect, which is dislocation. Twin boundary effect, defect. So the twinning is that is that's another type of defect that comes under line. Now, what's the next point? Line, surface, right? Yeah. So grain boundaries, twin boundaries come here as well. Yeah, grain boundary area defects. So these defects are, they are defects, but actually you can use these defects to your advantage. For example, you can use substitutional defect. So the way we make steels is nothing but substitutional defect. How do you think the carbon goes into the iron crystal? So it's basically you're putting an impurity in the crystal and changing the strength, the hardness, and so on and so forth. These are the you can use these defects for your advantage, and not just in tuning the mechanical strength, also in magnetics, in electrical materials. They play a very important role, especially dislocations. Okay, so we can control the percentage or the density of dislocations and the density of the point defects to our advantage, and make them and tune the properties of the materials just the way we want it by controlling the defects. Okay, the last one, grain boundaries, is used for catalysts. So for catalysis, you create grain boundaries such that you create a lot of surface. That what makes a catalyst. And now, I think we are out of time. I'll take one more minute just to show the difference between pure metal, substitutional alloy. So substitutional alloy is basically you are changing one of the atom with another atom, usually with similar atomic radii. So for example, nickel, cobalt, iron, they all have similar radii, and you can change this. And you don't change anything. When you take an XRD of a substitutional alloy, you don't see any difference. Okay? And same with interstitials. You take, you add some carbon to these elements, and if you take an XRD, you will see the same crystal structure, the pattern. The lattice parameters might slightly change because these can introduce some residual stress. Then this is both combined, interstitial and substitution. Okay, and sometimes the materials may not form any of these. If it forms these, you make a perfect alloy. But sometimes the solubility is not there. If you add cobalt will come and sit as a cluster in one corner, and it will have its own crystal structure. Right? So that is not a single phase alloy. It's immiscible, non-mixable material, and you see clumps of these, and the strengths of such materials are not good. Okay? Whereas when you form a single phase material, that becomes a good material. You can expect certain predictable properties. And here is how you see. So this is completely soluble, partially, these are grades. These are partially soluble. You see, this is completely, this will, if you take a XRD of this one, this will have a different crystal structure than this and then this. Okay? These two might have the same crystal structure, but this will have a different crystal structure. Whereas this one will have one crystal structure. XRD pattern will have one for this will have a mix of peaks. This will also have different peaks because it's completely solid. Okay? And that's the dislocation. I'll quickly show you this video and then we will take off. That's the end. Stress by moving the dislocations by doing thermal treatment, right? So dislocations can annihilate one another. Dislocations have directions. So when you increase the temperatures, two dissimilar dislocations can come together and completely disappear. Okay? When you do that, you are decreasing the dislocation density. So when you decrease the dislocation density, you are basically increasing the slip length, which means you can increase the plastic deformation. Okay? So that is nothing but increasing the ductility. And when you anneal a material, you are basically removing dislocations and improving the ductility. Okay? So that's very simple. I mean, it's quite widely used, where you can actually control the dislocation density to a point where you want to get the required property you want, not just strength. That's what we also can do that for electrical property, magnetic property, optical property, and so on and so forth. So all these. So I hope you got an idea now how composition, right? Next is atomic arrangement, right? Next is processing parameters. Next is engineering defects. Then the thermal treatment. You can use all these parameters to get a material property that you want. And the material property is, it could be increasing the hardness in a diesel engine so that it can take higher pressure, or it can be a ceramic in a turbine that needs high temperature withstanding, right? Or it could be a magnetic material that holds the magnetic energy so that it can use the neodymium ion boron magnets, right? That can produce the right sound or can produce a high torque, as in the electric vehicles, right? So that's, hope that gives you a good idea of what materials engineering can do, right? Now we'll go into specific functional material. So this is the foundation of material science, and now with these concepts, we will change the properties of functional material. Okay, I think that's the end of it. Sorry, it took a little longer because we started a little late. So we'll go take a break for guys. It's
Yes.
a tea time or
Yeah,
what?
it's a break.
Okay.
Thank you, sir, for the lecture. We will now break for tea. Volunteers are requested to guide all the participants to the foyer for tea. Following the tea, we will be having our demo 2 slot, which will be held in CIL 011. All participants are requested to arrive to the venue at the requested time for the next session. Volunteers are requested to guide them accordingly. Thank you.
So should I just get it for movies?
Yes.
Why?